Hi, welcome back to Statics 1. What I want to talk about now are what's called two force members, because these are essentially members, and you'll hear the word member a lot. It's kind of an odd term, but you'll see that in the textbook. Essentially, a member is, it's either like if you think about like from a structural standpoint, it's either like a beam, which is essentially usually horizontal. It could be a horizontal component within your structure, and a column, which is essentially a vertical structure. So that's what a member is. Member is just a piece of your structure that you'll be looking at. So like for a truss, it could be diagonal. We call those beams or columns. I think those are beams or truss components. All right, anyway, so a member, so what is a two-force member? So in this case, we're dealing with what's called two-force members. So, what do you think it means? It means a member which has two forces applied to it. And so I'm going to draw this member, and I'll draw it with like force A over here, and force B, I'll draw it essentially. I haven't drawn it in any particular sort of random directions. And in order for this thing to be in equilibrium, right, the sum of the forces in the x direction have to be equal to 0. The sum of the forces in the y direction have to be equal to 0. And the sum of the moments about a point, I'll just say A, equals 0. So this is our equilibrium condition. And again, I'm only showing x and y, so this is like a coplanar system. So this will only be a system where all the forces are in the x and y direction. In the x and y plane. So if this were the case, let's essentially look at this one first, the sum of the moments being equal to 0. If you look at this problem, okay, let's look at that case where we're looking at the sum of the moments about A equal to 0. So, and I'll do this in kind of a formal way, which will have first f of A times its moment arm, and if this is our point A, which is why I call that f of A, and this is our point B, and we have our f of B, I think it's obvious that there is no moment arm, so there's no contribution at this point, so we have a 0 value. Now, so if that contribution is 0, and if there are only two forces applied, then the contribution at this location has to be equal to 0 as well. So if we had equal to, so I'm going to add on over here, we're going to have plus f of B times its perpendicular direction. We can find the perpendicular direction. We can do some algebra. We can do some geometry. So here's the line of action of B, and we can find its perpendicular distance here, and we would essentially have f of B times this value here, which we'll call D. But you see that in order for this to be 0, well, this is obviously 0. This contribution has to be 0. But if f of B is not a 0 force, then the value of D has to in fact be 0. So in order, the only way you can have a moment arm D of 0 would be if this force were essentially in the direction of the axis of the two member force. And we could do this if we had done the opposite. If I'd written this as sum of the moments about B equals 0, then we would essentially find the same conclusion now, that this force has to be along that axis. Okay, so what it's telling us is that the direction of the vectors at either end of our two-force member has to be along the axis, or it has to be essentially in opposite directions. Otherwise, they're going to have some moment. You'll always have a moment, and this thing will start rotating, which means it's not in equilibrium. All right, so as long as we have this case where they're opposite directions, if we think about it, we realize that the force They actually have to have equal in magnitude. Because if one of these is of greater magnitude, then this is not in equilibrium, and this thing's going off in this direction, right? If the f of A is greater than f of B, it's not in equilibrium, it's moving off in this direction. So it's telling us two things. I guess, let me just kind of summarize what all this sort of thought process is telling us. First of all, is that, and this is for two force members, which is any member which has two forces applied to it. One is that the forces are opposing direction. Okay, and in this case, if you have a straight member, then they're going to be along the axis, and the magnitude of the forces is going to be equal and in the opposite direction. So they're going to have equal and opposite magnitude. I'll just write they'll have the same magnitude. We already said they're in the opposing direction, so we know that they're opposite, but they're going to have the same magnitude, our two forces. And let me just make it more general. In this case, I've drawn it for a straight component. You could have a curved component like this. So imagine that this is a solid member, but instead of being straight, it happens to be curved. The forces are going to have to be the same thing. They're going to have to, and again, we'll call this A. Excuse me, I'll call it B since we have B here. Now A here. But we're going to have the forces are going to have to be the same thing. They're going to have to be essentially in the opposing direction. In other words, they're going to be parallel, and they're going to have the same magnitude, so that we'll have no translation, and we'll have no rotation. In other words, they're in equilibrium. And that's the point, that they're in equilibrium. So this is really useful when we're dealing with structures or trusses, for example. So if we have a truss like this, and I'll just make it very simple. Here's our truss, and let's put a support here. So we have a roller at this end, we have a hinge at this end, and let's say we just want to draw the free body diagram, and I'm going to put forces on here. And we're very careful when we're doing this analysis, structural analysis of trusses, at least in statics 1, we're always going to be careful to only apply the forces at the joints. In other words, we have members, which are the lengths, and the joints are at the individual points. We're only going to apply them at those points. So let's look at this particular member here. So in the general case, if we didn't know it was a two-force member, we would essentially have to define 4 forces, and I'm going to give these letter A and B. So I'll put an A here, a B here, A here. So it's going to have an AX value, an AY value, a BX value, and a BY value. Now, since this is in fact a two-force member, meaning forces are only applied at one end and at the other end, and it really is, if you think about it, actually, you might think, well, look, this joint, this member here is applying force, that one's applying force, that one's applying force, but we're really going to look at the resultant force. The resultant force from all 3 of these other members imposed on point B, that's going to be essentially 1 point. Same here. We have a force caused by that member, we have the support reaction, but essentially we have only a single resultant force at that end. So we have a singular force, resultant force at the A end, single resultant force at the B end. That makes this a two-force member. The only way it would not be a two-force member if we were to apply a force in the middle, and that would make it a three-force member, which is an entirely different animal. So what can we say about this is that we can actually reduce this. This will be the free body diagram, and I write it as FBD, free body diagram, for this AB member, and it has 4 unknown reactions. But we can actually reduce this to 2 reactions because we know that they're going to be equal and opposite directions. And this one we'll just call force B and force A. And we know actually the angle, and we just have to calculate the magnitude of forces. And this member we know to be, we call this pure tension or pure compression, because there's no like bending to it. So that's the sort of interesting analysis of two-force members. So if you see a two-force member and you're drawing this free body diagram, you can always simplify it from this. You could write it up like this, but it's very often easier to analyze it by writing the free body diagram with just 2 forces instead of 4 forces. All right, so if you have any questions on this, please get back to me, and I'm happy to answer them. Otherwise, I will see you in class.